y double dashed minus 6y dashed plus 5y equals 3e to the power 4x, and here's the initial conditions here. So let's turn our attention to the solution of the associated homogeneous equation then. So here we simply can write y double dashed minus 6y dashed plus 5y equals 0. The auxiliary equation in this case is lambda squared minus 6 lambda plus 5, which has roots lambda minus 5, lambda minus 1, isn't it? Equals 0. And that implies lambda, it has two distinct roots. The first one is at value 1 and the other value is at value 5. So this is case 1, real distinct roots. So case 1 gives YH, which we'll write in explicitly now, a e to the one of the roots, so 1x, plus be to the other root, which is 5x. So that's YH done then. Now we turn our attention to YP. So YP now, 3e to the 4x, let's go back to our table. E to the 4x, 3, we try ae to the 4x, don't we? So we try y equals ae to the 4x. In this case, y dashed, e to the something, the 4 will come down onto, it'll be 4a e to the 4x. And y, if we differentiate again to get the second derivative, another 4 will come down because it's a function of a function, and the something differentiates to 4, so it's going to be 16a e to the 4x. So substitution now gives, so let's just put our screen back up, adjust it here. So we got to sub it in the thing at the top. Y double dashed, 16a. Notice there's an e to the 4x common throughout, so we'll keep that outside a bracket, make life a bit easier for ourselves. So one of these, which is 16a, minus 6y dashes. Y dashed is 4a, and then plus 5y, and y is a. All times e to the 4x is equal to 3e to the 4x. So that implies we've got 16a plus 5a is 21a minus 24a. So you've got 21a minus 24a is minus 3a, isn't it? Equals 3. The e to the 4x's can cancel both sides, so that tells us a is minus 1. There we go. There's a. So I'm just going to double check that. 16, take 24 plus 5. 16 plus 5 is 21. Take 24 is minus 3a. Minus 3a equals 3. A equals minus 1. So, that's yp done. So we can write down the general solution now. Y equals yh, ae to the x, plus b, e to the 5x, and then plus yp, which was minus 1, e to the 4x. Now we can differentiate y dashed. Let's just write that down here while we're at it. A to the x then. The 5 comes down, plus 5b, e to the 4x, and then the 4 will pop down when we differentiate, minus 4 e to the 4x. There we go. So initial conditions y, the first one, I'll put in y naught equals 2. So y naught equals 2 gives, let's see what we get here. So when x is 0, y is 2, so 2 equals, x is 0, e to the 0 is 1, so that's a. Similarly, it's b times 1, isn't it? Which is b, minus e to the 0, which is 1. So that tells us then that a plus b is equal to, move the 1 over to be with the 2, becomes plus 1. 2 plus 1 is 3. So there's our first equation. I'll put it in a box so that we know where it is. Okay, that's the first one. Now let's apply the second initial condition, which is y dashed naught equals 1. So let's do that here. Y dashed naught equals 1 gives. So when x is 0, y dashed is 1. So there's 1 equals. ae to the naught is just a. 5be to the naught is just 5b. And then we've got minus 4e to the naught, which is just minus 4. So that tells us then that a plus 5b is equal to, move the minus 4 over to be with the 1, plus 4. 4 plus 1 is 5. This is equation 2. There we go. So that's good. 2 take 1 because these are bigger than those and the a's will disappear. So 2 take 1 then. 2 take away 1. What does that give? That take that is 4b. And this take that is 2. So b is a half. Capital B is a half. And then so a is equal to 3 minus b. 3 minus a half is 2.5. And you can write that as 5 over 2 if we wish. So there's A. So there's A and B then. And now we can write our particular solution then, can't we? So that's the initial conditions done. So y equals then, the solution is here. So A is 5 over 2 e to the x plus b, which is a half, e to the 5x, and then we've got minus e to the 4x.